In July of 2023, a team of planetary scientists published a paper in the journal Nature. The paper described something they had found on the far side of the moon, something that, in their own words, should not be there. Something that broke the textbook explanation of how the moon works. Something that one of the lead researchers described as being puzzled when they found it. The discovery was made using data from Chinese orbital spacecraft. It was confirmed by multiple independent instruments. It was peer-reviewed and published in one of the most prestigious scientific journals in the world. And it raised a question that nobody has fully answered since. How did this get here? And what does it tell us about a side of the moon that, for most of human history, nobody has ever seen? Tonight, we are going to go to the far side of the moon. We are going to look at everything that has been found there, the anomalies, the things that do not fit, the discoveries that have quietly rewritten what scientists thought they understood about our closest neighbor in space. And we are going to ask the question that all of it points toward. The far side of the moon is different from the near side in ways that are documented, confirmed, and still not fully explained. And the more we look, the stranger it gets. The more we look, the stranger it gets. That is not a dramatic phrase chosen for effect. That is the actual experience of the scientists who have spent their careers studying this object. Every mission that has gone to the moon, every instrument that has mapped it, every sample that has come back from it has revealed new layers of complexity, new things that do not fit, new discoveries that require new explanations. The moon is not the simple, dead, solved object that most people assume it is. It is an active scientific puzzle, and many of its most interesting pieces are on the side we could not see for most of human history. Before we go further, if this kind of content is what you come here for, take a second to subscribe. It helps this channel keep going. Now let us start at the beginning. For all of human history, the moon showed us only one face. Every night without exception, every full moon, every crescent, every quarter, the same face, always. The moon is tidally locked to Earth, meaning it rotates at exactly the same rate it orbits our planet. One rotation per orbit, the same hemisphere permanently facing us, the other hemisphere permanently facing away. Think about what that means. For thousands of years of human civilization, from the first cities in Mesopotamia to the first telescopes in Europe, from ancient astronomers in China and Egypt and Greece, to every generation that has ever looked up at the sky, nobody had ever seen the other side of the moon. Not once. It was not that it was hard to reach. It was that it was literally impossible to see. No telescope, no matter how powerful, built on the surface of Earth could ever show you what was on the other side. The moon was hiding half of itself from us for the entire history of our species. For the entire history of our species. Think about that. Every human being who ever lived until 65 years ago never saw half the moon. Not the ancient Greeks with their careful astronomical observations. Not Galileo with his first telescopes. Not the astronomers of the 18th and 19th centuries who mapped the stars in extraordinary detail. Not anyone. Half the moon was simply invisible, permanently hidden, there and unreachable at the same time. The far side of the moon was not seen by human eyes until 1959. The Soviet spacecraft Lunar 3 flew around the moon and transmitted the first photographs back to Earth. Those photographs were blurry, low resolution, difficult to interpret, but they showed something immediately and unmistakably. The far side looked nothing like the near side, nothing at all. The near side of the moon, the face you see every night, is marked by large, dark regions called Maria. That word is Latin for seas. Early astronomers named them seas because they thought those dark expanses might be bodies of water. They are not water. They are vast, ancient plains of solidified lava, dark basaltic rock that formed billions of years ago when volcanic activity on the moon was still active. These dark plains, these maria, cover about 31% of the near-side surface. They are what gives the moon its familiar appearance, the pattern of dark and light that people have been staring at since before recorded history. The face in the moon. The man in the moon. Whatever you call it, whatever shape you see in those dark patches, it is all made of ancient lava. The far side has almost none of this. The far side is almost entirely covered with ancient, heavily cratered highland terrain. Bright, rough, battered by billions of years of impacts, looking completely different from the familiar face we see every night. The maria that define the moon as we know it, that give it its recognizable face, are almost entirely absent on the other side. You would not recognize the far side as the same object. If you saw the near side and the far side by side without knowing what you were looking at, you might think they were two different worlds. Two different worlds, that is not an exaggeration. The near side and the far side of the moon look so different from each other that the first scientists to see Lunar 3's photographs were genuinely startled. They had expected some differences. They had not expected this. They had not expected a face so alien, so utterly unlike the familiar moon, that it felt like a separate object entirely. This difference is not a minor variation. It is not something you need instruments to detect. It is one of the most dramatic geological differences on any large body in the solar system. And after more than 60 years of study, scientists do not have a complete explanation for it. We have studied the moon longer than we have studied anything else in space. We have sent spacecraft to orbit it, land on it, drive across it, drill into it. We have brought back hundreds of kilograms of lunar rock and analyzed it in laboratories with every instrument available. We have mapped the moon's gravity field, measured its internal structure, studied the seismic waves that move through it using instruments left by the Apollo missions. We have mapped the entire surface at 1 meter resolution. We have measured the isotopic composition of lunar minerals with mass spectrometers. We have studied the moon from every angle, with every tool, for 60 years. And we still do not fully understand why the two sides look so different. That is where we are starting tonight. Not with speculation, not with theories about things that cannot be verified, with a genuine documented scientific mystery that has sat at the center of lunar science for more than 60 years and has not been resolved. A mystery confirmed by every mission, deepened by every discovery, still open after 6 decades of the most intensive study any object beyond Earth has ever received. Now, let us go through what we know, what has been found, what has been confirmed, and what it means. The moon formed roughly 4.5 billion years ago. The most widely accepted theory, supported by extensive evidence including the isotopic composition of lunar rocks, is that a Mars-sized body called Theia collided with the young Earth. The collision was catastrophic. It ejected enormous amounts of material from both Earth and Theia into space. That material gradually coalesced under gravity and became the moon. In the earlier stages of the moon's existence, the entire body was largely or entirely molten. Scientists call this the lunar magma ocean, a global ocean of liquid rock covering the entire object, hundreds of kilometers deep in places. The entire moon from pole to pole, a world of liquid fire. As the magma ocean cooled over millions of years, different materials separated out. Lighter minerals floated upward and formed the crust. Denser materials sank. The moon differentiated into layers, crust, mantle, core. This is the same basic process that built Earth's internal structure and the structure of every rocky planet in the solar system. It is well understood. It is supported by physics, chemistry, and direct observation. But the cooling did not happen the same way on both sides. This is where the mystery begins. The crust that formed on the far side of the moon is thicker, significantly thicker. Scientists using gravity data from NASA's Grail mission, two spacecraft that orbited the moon in precise formation and measured tiny variations in its gravitational pull, found that the far side crust is typically 60 to 80 kilometers thick. The near side crust is typically 30 to 40 kilometers thick. The far side has roughly double the crustal thickness of the near side, a global asymmetry built into the very structure of the moon from the earliest period of its history. Double the thickness. Let that land, not 10% thicker, not 20%. Double. On one side of the same object, the crust is twice as thick as on the other side, built in from the beginning, not caused by later impacts or volcanic activity, fundamental to the structure of the moon itself. And scientists are still debating exactly why. One theory, published in the journal Nature Geoscience in 2022 by Nan Zhang and colleagues at Peking University, proposes that the South Pole Aitken impact fundamentally reshaped the moon's interior by triggering a global mantle overturn. The impact on the far side pushed hot, dense titanium-rich material from below the crust to migrate towards the near side, where it sank into the mantle in what the researchers describe as sheet-like cascades. This migration of dense material away from the far side and toward the near side changed the thermal and chemical balance of the two hemispheres in ways that are still playing out billions of years later. Another theory suggests that the early moon may have had a second, smaller companion moon. This second moon orbited Earth alongside the primary moon for tens of millions of years, before eventually merging with it in a slow collision that built up the near side crust. The collision was gentle by planetary standards, more of an accretion than an impact, but it would have added enormous amounts of material to one side of the moon and created the crustal asymmetry we observe today. Each of these theories is grounded in real physics. Each has been published in major scientific journals, and none has been definitively confirmed. The origin of the moon's asymmetry remains one of the central unsolved problems in planetary science. Now let us talk about the chemistry, because it is just as strange as the structure, maybe stranger. The near side of the moon is rich in a specific group of elements that scientists call creep. The acronym stands for potassium, rare earth elements, and phosphorus. These elements have a specific chemical property. They do not fit into the crystal structures of the minerals that form first as a magma ocean cools. They are the chemical leftovers, the materials that get pushed out and concentrated as the solidification process proceeds. They end up in the last liquid rock, the final dregs of the magma ocean, highly concentrated because everything else has already crystallized out. The last liquid, the richest liquid, the liquid loaded with everything that could not crystallize anywhere else. On the moon, most of these elements ended up on the near side. The near side has extraordinarily high concentrations of radioactive thorium and potassium. Concentrations that are visible from orbit, that glow in gamma-ray surveys, that saturate the near-side geology in ways that are immediately apparent to any instrument sensitive to these elements. The far side has almost none of this, almost completely depleted of the elements that the near side has in abundance. Almost completely depleted. The same elements that define the near side chemistry are nearly absent on the far side. The two hemispheres of the moon have profoundly different chemical compositions. Not slightly different, profoundly, dramatically different. as if the same object was made of two different materials on two different sides. This matters enormously, because radioactive elements like thorium and uranium generate heat as they decay. The near side of the moon has been internally heated by these elements for billions of years. That extra heat kept the near side's interior molten longer than the far side. It kept the magma flowing. It filled the vast basins with dark lava, creating the Maria we see today. The far side, lacking these heat sources, cooled faster and earlier. Its volcanic activity ceased sooner. Its ancient craters were never flooded with lava. They remain as they were, battered and bright. Billions of years of impact history written on a surface that never changed. This is the explanation most scientists accept for why the two sides look so different. Different distributions of radioactive elements led to different thermal histories. Different thermal histories led to different volcanic histories. Different volcanic histories led to very different surfaces. It is a coherent story supported by data that explains the major features of the moon we observe. But it does not explain everything. And the things it does not explain are the ones that have made the far side increasingly strange, the more we look. In July 2023, a team of researchers led by Matt Siegler of the Planetary Science Institute published a paper in the journal Nature. They had been using microwave temperature data from Chinese orbital spacecraft, the Chang'e-1 and Chang'e-2 orbiters, to map the heat coming from beneath the lunar surface. Microwave radiation can penetrate the top few meters of the lunar surface and reveal the temperature at depth. It is a different kind of measurement than surface temperature. It tells you what is happening below, not just above. And at a location on the far side called the Compton-Belkovich region, named for two craters nearby, they found something that stopped them cold. The ground was putting out heat at about 180 milliwatts per square meter. The average heat flow in the surrounding far side highlands is about 9 milliwatts per square meter. The Compton-Belkovich region was producing 20 times more heat than the terrain around it, about 10 degrees Celsius warmer at depth than anywhere nearby. In Siegler's own words, it was glowing hot compared to anywhere else on the moon. Glowing hot, 20 times the surrounding heat output, on the side of the moon that was supposed to have been cold for billions of years. This region had been flagged as unusual before. In the late 1990s, scientist David Lawrence, analyzing data from NASA's Lunar Prospector mission, had noticed an anomalous bright spot of thorium gamma rays coming from this location. Thorium, on the far side, where thorium was not supposed to be concentrated. The region had been noted and wondered about for over 20 years. Papers had been written about it. Scientists had discussed it. But nobody had fully understood what was causing it, what was producing the thorium signal, what was underneath. The new microwave data revealed the answer. The heat and the thorium were coming from an enormous mass of granite buried beneath the surface. A granite body approximately 50 kilometers in diameter and up to 20 kilometers deep. A batholith in geological terms. A large solidified mass of granite that formed underground and never reached the surface. 50 kilometers in diameter, 20 kilometers deep. A block of granite the size of a major metropolitan area buried on the far side of the moon. Granite is extremely rare in the solar system outside of Earth. On Earth, granite forms under specific conditions. It requires multi-stage melting and remelting of rock. It requires water to lower the melting point of minerals and allow complex chemical fractionation over extended periods. It requires the kind of geological processing that, on Earth, happens in subduction zones where one tectonic plate dives beneath another, carrying water-bearing minerals deep into the interior where they melt and differentiate. These conditions, liquid water and plate tectonics, are not supposed to exist on the moon. The moon is dry. The moon does not have plate tectonics. The moon should not be able to make granite. The Apollo missions brought back only a few tiny grains of granite across all of their combined samples. Trace amounts, scientific curiosities, anomalous specks in otherwise basaltic collections. Not a batholith 50 kilometers across buried on the far side. Ziegler said directly after the discovery, all the textbook ways of making granite involve processes that only happen on Earth. He said, if you do not have water, it takes extreme situations to make granite. He said, here is this system with no water, no plate tectonics, but you have granite. Was there water on the moon, at least in this one spot? Or was it just especially hot? Was there water on the moon, in this one spot? That question, from a peer-reviewed publication in Nature, from a credentialed planetary scientist at a major research institution, tells you something about how unexpected this discovery was. The researchers were not just noting an anomaly, they were questioning fundamental assumptions about what the moon is and what it has experienced. Those questions remain open. The researchers said they need the geologists to figure out how you can produce this kind of feature without water, without plate tectonics. They admitted directly that the existing textbook explanations do not work. Not that they need refinement, not that they need more data. That they do not work. The textbook explanation for how the moon formed and evolved does not produce a 50-kilometer wide granite batholith on the far side. This was published in Nature. The discovery was confirmed by multiple independent instruments. And the lead researcher said directly, we were puzzled when we found it. Puzzled, that is the word. Not excited. Not thrilled in the way scientists are when they confirm what they expected. Puzzled. Because this was not expected. Because this did not fit. Because the moon was not supposed to have this. Now let us talk about what is buried beneath the largest crater in the solar system. The South Pole Aitken Basin is the dominant feature of the far side of the moon. It is enormous. It is approximately 2,500 kilometers in diameter. The continental United States from coast to coast is about 4,500 kilometers wide. The South Pole Aitken Basin is more than half that width. It is one of the largest confirmed impact craters in the entire solar system. It is the largest, oldest, and deepest basin on the moon. Scientists estimate it formed approximately 4.3 billion years ago, when the solar system was young and large impacts were common. The impact that created this basin was beyond anything in human experience. An asteroid or protoplanetary body estimated to be between 150 and 200 kilometers in diameter struck the moon at approximately 12 to 15 kilometers per second, 150 to 200 kilometers in diameter. That is roughly the distance from London to Birmingham. An object that large hitting the moon at 12 kilometers per second. The collision released energy that defies ordinary description. It excavated material from deep within the moon, from the lower crust, and possibly from the upper mantle itself. It sent debris across the entire moon and beyond into space. It may have temporarily destabilized the moon's rotation. It permanently changed the moon's chemistry by excavating mantle material and distributing it across the surrounding terrain. The lowest point on the moon is inside this basin, about 9 kilometers below the surrounding highlands. The basin's rim forms some of the highest mountains on the moon. The contrast in elevation across this single feature spans nearly 17 kilometers from the lowest floor to the highest peaks on the rim. 17 kilometers of vertical relief in a single impact structure. The Grand Canyon is about 1.6 kilometers deep. The South Pole Aitken Basin has 10 times that depth difference within its own structure. And yet, despite its enormous size and depth, the South Pole Aitken Basin was not flooded with lava the way the large basins on the near side were. It is not dark like the Maria. Its depth should have brought it close to or through the lunar crust, potentially allowing magma to well up from below. On the near side, that is exactly what happened in other large basins. Lava flooded them and created the dark Maria we see today. But in the South Pole Aitken Basin, it mostly did not happen. The basin floor never flooded at the same scale. Why not? Because of the creep asymmetry. The far side was drained of its heat-producing elements. Without those heat sources, there was not enough energy to keep the mantle molten long enough to flood the basin with lava after the impact. The far side cooled, the basin floor hardened, the crater remained. And it has been sitting there for 4.3 billion years, the largest impact structure in the solar system, essentially unchanged since the day it formed. But there is something stranger than the basin itself, something invisible from the surface, something that required the most precise gravity measurements ever made of the moon to detect. Buried beneath the basin floor, invisible from above, detected only by the tiny gravitational pull it exerts on spacecraft flying overhead, there is an anomalous mass. In 2019, scientists analyzing data from NASA's Grail mission announced the discovery of a massive, dense object buried beneath the floor of the South Pole Aitken Basin. Grail had mapped the moon's gravity field in extraordinary detail by measuring tiny variations in the separation between two spacecraft flying in formation. When one spacecraft was pulled slightly toward a region of higher mass, it would accelerate slightly, changing the gap between the two spacecraft by a measurable amount. By continuously measuring that gap to extraordinary precision, scientists could map every concentration of mass inside the moon. And, beneath the South Pole Aitken Basin, they found something unexpected. A mass concentration estimated to be about 5 times the mass of the Big Island of Hawaii. A dense, heavy object buried in the moon's mantle, below the crust, pulling the basin floor downward by more than half a mile. Its presence measurably affects the moon's gravity field. It is real. It has been measured by multiple analyses. It is sitting there. What is it? The most compelling explanation is that it is the metallic remnant of the asteroid that created the basin, still lodged in the moon's mantle after the impact 4.3 billion years ago. A chunk of dense, iron-rich impactor material that never fully dispersed, that sank into the mantle in the aftermath of the collision, and has remained there ever since. The largest impact crater in the solar system still has the impactor sitting inside it. Think about that. The collision happened 4.3 billion years ago. The asteroid hit the moon. The moon survived. The impactor sank into the mantle, and it is still there. After 4.3 billion years of sitting in the moon's interior, still measurable, still affecting the moon's gravity. A passenger the moon has been carrying since before complex life appeared on Earth. This object has never been directly sampled. We know it is there from gravity measurements. We know approximately how large it is and approximately how dense it is. But we have never touched it, never analyzed its chemistry, never confirmed exactly what it is made of. It sits more than 300 kilometers beneath the surface of the far side of the moon, beyond any drill or lander we currently possess. A mystery inside a mystery at the center of the largest crater in the solar system. Now, let us talk about the magnetic mystery of the far side. The moon does not currently have a global magnetic field. If you stood on the moon with a compass, it would not point consistently in any direction. The moon's core is no longer generating a dynamo field the way Earth's core does. The moon is magnetically quiet, magnetically silent. But the rocks tell a different story. The lunar crust contains regions of significant magnetization, patches of ancient rock that were magnetized billions of years ago and have retained that magnetization ever since. These regions produce detectable magnetic anomalies that spacecraft have mapped in detail. And the pattern of where those anomalies are located is strange. Very strange. They are not randomly distributed. They are concentrated on the far side of the Moon. Many of them are located at positions precisely antipodal to large impact basins on the near side. Antipodal means directly opposite. The point on the far side that is exactly opposite the Imbrium basin on the near side shows strong magnetic anomalies. The point opposite the Serenitatis basin shows magnetic anomalies. The points opposite several other major near-side basins show enhanced magnetization. Why would magnetic anomalies on the far side be located at points directly opposite large craters on the near side? The answer requires thinking about shockwaves. When a large asteroid impacts the Moon, it sends a shockwave through the entire body. That shockwave travels outward from the impact in all directions. It passes through the Moon's interior. And eventually, all those waves converge at one point on the other side, the antipodal point, where energy arriving from all directions meets simultaneously. The convergence at the antipode creates an intense zone of disruption. Rocks are fractured and remelted. Material is thrown about. And if the Moon had a global magnetic field at the time of the impact, the disrupted material would have been heated above the temperature at which magnetic minerals lose their orientation, and then cooled in the presence of the existing field, locking that field direction permanently into the rock. Like a photograph of the magnetic field taken at the moment of the impact, preserved forever. This mechanism explains why antipodal magnetic anomalies exist. But it raises a deeper question. How strong was the ancient lunar magnetic field? The magnetization locked into the rocks suggests it was strong. Stronger than current theoretical models of the ancient lunar dynamo predict it should have been. The Moon's core was not large enough, the models say, to generate a field as strong as the rocks appear to record. That discrepancy is not resolved. The rocks say one thing, the models say another. And the far side, having preserved its ancient magnetized crust without volcanic resurfacing, is the place where that discrepancy is most clearly readable. Now let us talk about the first physical samples ever returned from the far side of the Moon. On June 1st, 2024, China's Chang'e 6 spacecraft landed on the far side of the Moon in the Apollo Basin, a crater inside the South Pole Aitken Basin. It spent about 53 hours on the surface, drilling and scooping material from the ground. On June 25th, 2024, the return capsule landed in Inner Mongolia, China, carrying approximately 1.9 kilograms of material collected from the far side of the Moon. 1.9 kilograms, less than 2 kilograms. It does not sound like much, but it was everything. For the first time in history, human beings had physical samples from the part of the Moon that had been invisible to us for all of human history until 1959. For the first time, scientists could hold far side rock in their hands and analyze it in a laboratory with every technique available. Not orbital data, not remote sensing, not images, actual rock. The results began arriving in 2024 and 2025, and they confirmed something that had been hypothesized for decades, but never proven with actual material from the ground. The samples were approximately 2.8 billion years old. The chemistry of these rocks told a specific and important story. A team of researchers from University College London and Peking University analyzed the mineral composition of the samples and determined that the lava they came from had formed at a temperature of approximately 1,100 degrees Celsius. Near-side lavas, based on samples brought back by Apollo, had formed at temperatures about 100 degrees Celsius higher. The far-side lavas were cooler when they erupted, by a significant and measurable margin, 100 degrees cooler. At depth, in the mantle, where the lava formed, the far side was 100 degrees cooler than the near side when these rocks were made 2.8 billion years ago. The asymmetry runs through the entire Moon, from the surface all the way down into the interior where the rock melts. Professor Yang Li of University College London stated directly, "The near side and far side of the Moon are very different at the surface and potentially in the interior. We call it the two-faced Moon. A dramatic difference in temperature between the near and far side of the mantle has long been hypothesized, but our study provides the first evidence using real samples." First evidence using real samples. Not models, not theory. Real rocks from the ground, analyzed in a laboratory, showing that the Moon is genuinely and measurably different inside on the two sides. The two-faced Moon. Different on the surface, different in the crust, different in the mantle. PhD student Xuelin Zhu said, "These findings take us a step closer to understanding the two faces of the Moon. They show us that the differences between the near and far side are not only at the surface, but go deep into the interior. Deep into the interior. A fundamental split running through the entire object, from the outermost crust to the deep mantle. The Moon has two faces in every sense." The Chang'e 6 samples also revealed something else. Chinese scientists from the Institute of Geology and Geophysics showed that the South Pole Aitken impact itself had left chemical traces in the rock. The massive collision 4.3 billion years ago had heated material deep in the Moon and driven off certain volatile elements. Those losses were preserved in the isotopic ratios of the far side rocks, readable today with sensitive instruments. A record of the most violent event in the Moon's history, chemically encoded in the rock that formed in the aftermath. The collision happened 4.3 billion years ago and left a message that we only just learned to read. Now let us talk about the ice. The Moon's south pole is where the South Pole Aitken Basin meets the permanently shadowed craters at the pole itself. And those permanently shadowed craters are among the most scientifically important places in the solar system. Because the Moon's axis is tilted only about 1.5 degrees relative to its orbit, the floors of certain deep craters near the poles never receive sunlight. Not seasonally dark the way polar regions on Earth are. Permanently dark. Never. Not once in billions of years. The floors of the deepest polar craters have not seen a single photon of sunlight since the craters formed. The temperatures in those floors can reach -200 degrees Celsius or colder. Some of the coldest measured surfaces in the entire solar system. Colder than the surface of Pluto. In such extreme cold, volatile materials that arrived on the Moon from comet and asteroid impacts billions of years ago can be preserved essentially forever. The cold is so extreme that no thermal process can mobilize these materials. They are frozen in place, locked into the ice, preserved exactly as they arrived, including water ice. NASA confirmed the presence of water ice in permanently shadowed craters at the Moon's poles in 2018, using data from the Moon Mineralogy Mapper instrument aboard India's Chandrayaan-1 spacecraft. The confirmation was published in the Proceedings of the National Academy of Sciences. Water ice. In craters at the Moon's south pole, frozen in permanent darkness for billions of years. And in October 2024, a new study analyzing data from NASA's Lunar Reconnaissance Orbiter found that ice deposits at the South Pole are more widespread than previously thought. Lead author Timothy McClanahan of NASA's Goddard Space Flight Center stated, "We find that there is widespread evidence of water ice within permanently shadowed regions outside the South Pole, towards at least 77 degrees south latitude. The ice is not confined to a few specific craters. It is distributed across a broad region. more widespread than previously thought. The picture keeps expanding. Every new measurement reveals more ice than the last measurement showed. This water ice is not just a practical resource for future explorers, though it is that. It is a scientific archive. The isotopic composition of that water could tell us where it came from, whether it arrived on comets or asteroids, whether those sources are the same ones that brought water to Earth, whether the early solar system was wetter or drier than current models predict. The answer to some of the most fundamental questions about the history of our solar system may be frozen in the permanently shadowed craters at the south pole of the Moon. Planetary scientist Paul Hayne described the water ice question as the Holy Grail from his point of view. If we can get a sample, he said, we could maybe find out where that water came from, and then, by extension, where Earth got its water. The Moon and Earth formed together. What the Moon tells us about the delivery of water to the inner solar system tells us about Earth too. But getting that sample has proven remarkably difficult. Despite decades of orbital detection and multiple confirmed discoveries of ice, no mission has yet landed in a permanently shadowed crater, drilled into the ice, and returned a sample for laboratory analysis. The craters are in perpetual darkness. Any lander there cannot rely on solar power. The terrain inside them is rough and unmapped, because light has never illuminated it. The instruments that detected the ice were not designed for this purpose, leaving ambiguity in the data. Norbert Schurghofer, a scientist who studies lunar volatiles, stated in late 2025, "There has been shockingly little progress about ice due to the lack of landed missions to the polar regions. Scientists are trying to tease out information from data collected for other reasons, from instruments never designed to detect lunar volatiles. What we need is definitive measurements. We know the ice is there. We cannot yet tell you exactly how much. We cannot yet tell you exactly where in sufficient detail to target a landing. We cannot yet tell you what its composition reveals about the early solar system." All of those answers require going there. The Artemis program is going there. NASA's planned landing sites for Artemis crewed missions are at the south pole of the Moon, on the edge of the South Pole Aitken Basin, near the permanently shadowed craters. The astronauts who land there will be the first humans to stand at the south pole of the Moon. The first humans within reach of craters that have not seen sunlight since they formed. The first humans with the potential to collect definitive samples of polar ice and bring them home. Jeffrey Andrews Hanna, a planetary scientist at the University of Arizona who has published extensively on the South Pole Aitken Basin, stated that when Artemis astronauts land near the South Pole, they will find themselves in an unexpected treasure trove of clues about the Moon's earliest history. The landing sites are in material excavated from deep within the Moon by the South Pole Aitken impact. Material that has never been sampled. Material that may include fragments from the lunar mantle. The deepest material ever excavated in the Moon's history. Andrews Hanna described the distribution of material around the South Pole Aitken Basin as telling a story about the final stages of the lunar magma ocean. The thick, growing crust on the far side pushed the remaining liquid rock toward the near side, like toothpaste being squeezed out of a tube. The near side ended up enriched in every element that could not crystallize. The far side was left drained. But the Compton-Belkovich granite batholith does not fit this story. If the far side was drained, how does a 50-kilometer-wide granite batholith end up there? On the wrong side, glowing with heat, saturated with thorium, made of rock, the models say, cannot form there. The researchers who published the discovery said they need the geologists to figure it out. They said the existing explanations do not work. They said plainly, we do not know how this happened. But Before we talk about where we are going, let us talk about how we got here. Because the history of how humanity learned to reach the moon and what we found when we did is a story that most people think they know, and almost nobody actually knows in full. The textbook version is simple. We launched rockets, we landed on the moon, we came home. But the real story is far stranger, far more difficult, and far more interesting than that. Let us go back to the beginning. The first spacecraft ever to reach the moon was not American. It was Soviet. Lunar 1 launched on January 2nd, 1959. It was supposed to hit the moon. It missed. Due to a timing error in the launch sequence, it flew past the moon at a distance of about 6,000 kilometers and became the first human-made object to escape Earth's gravity and enter orbit around the Sun. An accidental solar satellite, the first spacecraft to leave Earth's gravitational influence. It was aiming for the moon and missed, and in doing so it became something nobody had planned for. Lunar 2, launched in September of the same year, did not miss. It became the first spacecraft to impact the surface of another celestial body, slamming into the moon at about 3.3 kilometers per second on September 14th, 1959. The spacecraft carried Soviet pennants, small metal spheres engraved with the USSR emblem, intended to survive the impact and remain on the surface as markers. Some of them may still be there. Somewhere on the surface of the moon, there are small pieces of Soviet metal that have been sitting undisturbed for more than 65 years. And then came Lunar 3, the mission we already mentioned, the one that showed humanity the far side for the first time. October 1959. 3 significant lunar firsts in a single year. That was the pace of the space race at its height. The Americans were not far behind, but they were struggling. The early Ranger missions, designed to crash into the moon while photographing the surface on the way down, were plagued with failures. Ranger 1 through Ranger 6 all failed for various reasons. Ranger 1 and 2 failed to reach the correct orbit. Ranger 3 missed the moon entirely. Ranger 4 hit the moon, but its systems had failed and it returned no data. Ranger 5 lost power and flew past. Ranger 6 reached the moon, but its cameras had been accidentally damaged during launch and returned nothing. 6 consecutive failures, each one a national embarrassment in the context of the space race. Each one a reminder that space is not forgiving of engineering errors, manufacturing defects, or bad timing. The moon was proving difficult to reach, even when you just wanted to crash into it. Ranger 7 finally succeeded in July 1964. It transmitted 4,308 photographs of the lunar surface in the final 17 minutes before impact. The photographs were more detailed than anything a telescope on Earth could produce. They showed the surface clearly, the craters, the rocks, the textures, for the first time in a resolution that felt real. The project team at JPL, watching those photographs come in, described the moment as overwhelming. After 6 failures, after years of work, they were finally seeing the moon up close. Rangers 8 and 9 followed successfully in 1965. The path was open. Meanwhile, the Soviets were pushing further. Lunar 9, in February 1966, became the first spacecraft to make a soft landing on the moon and survive. It settled onto the surface in the Oceanus Procellarum region on the near side and transmitted the first photographs taken from the surface of the moon. Those photographs showed a rocky, barren landscape, littered with small stones, stretching to a horizon that seemed impossibly close because the moon is so much smaller than Earth. They were the first ground-level photographs ever taken on another world. This mattered more than it might seem. Before Lunar 9, there was genuine scientific uncertainty about what the surface of the moon was like up close. One influential theory, advanced by scientist Thomas Gold, held that the moon's surface was covered in a deep layer of fine electrostatically charged dust, accumulated over billions of years, that would swallow anything that tried to land on it. A spacecraft, a lander, potentially even an astronaut, might simply sink into a deep, inescapable powder. Lunar 9 proved that the surface was solid enough to support a spacecraft. The deep dust theory was wrong. The moon could be landed on. The Americans reached the same conclusion with Surveyor 1, which landed in June 1966, and also transmitted surface photographs from the near side. The path to a crewed landing was clearing. The Soviet lunar program kept pushing. Lunar 10, also in 1966, became the first spacecraft to enter lunar orbit. Lunar 12 and 14 followed as orbiters. Lunar 13 landed and used a penetrometer, essentially a spike pushed into the soil, to measure the mechanical properties of the lunar surface for the first time. The surface was firm, supportable, suitable for landing. And then came the orbiters. The American Lunar Orbiter Program, 5 missions launched between 1966 and 1967, systematically photographed the moon from orbit in detail sufficient for landing site selection. They mapped 99% of the lunar surface. They produced photographs of resolution and quality that remained the basis of lunar mapping for decades. 5 missions, all successful, all returning an extraordinary photographic archive of the moon from orbit. These missions found the landing sites for Apollo. Without them, the crewed landings could not have happened. The Surveyor program continued alongside the orbiters. Surveyors 3, 5, 6, and 7 all landed successfully and studied the surface in detail. Surveyor 7 landed near the crater Tycho, far from the equatorial band that the crewed missions would target, and studied a geologically different and scientifically interesting region of the near side. Surveyor instruments analyzed the chemical composition of the surface, measured its bearing strength, studied its thermal properties. They were advanced scouts testing the terrain for the humans who would follow. All of this happened in less than a decade. From Lunar 1 missing the moon entirely to Surveyor 7 doing detailed chemical analysis of the surface. Less than 10 years. The pace of it, when you look at the full timeline, is almost impossible to believe. And then came Apollo. Apollo 8 in December 1968 was the first crewed spacecraft to leave Earth orbit. The first crewed mission to orbit the moon. 3 astronauts, Frank Borman, James Lovell, and William Anders, rode a Saturn V rocket to the moon, entered lunar orbit on December 24, 1968, completed 10 orbits, and came home. They were the first human beings to see the far side of the moon with their own eyes. They were the first human beings to see the whole Earth from deep space. William Anders took the photograph known as Earthrise, the image of Earth rising above the lunar horizon, which became one of the most widely reproduced photographs in history. Apollo 10 in May 1969 was the final rehearsal. The command module orbited the moon while the lunar module descended to within 15 kilometers of the surface before separating the descent stage and returning to dock with the command module. Everything was tested except the final landing. The systems were verified. The procedures were confirmed. The path was clear. Apollo 11 launched on July 16, 1969. Neil Armstrong and Buzz Aldrin landed in the Sea of Tranquility on July 20, 1969, at 2017 UTC. Armstrong stepped onto the surface at 2:56 UTC on July 21st. They spent approximately 2.5 hours on the surface during their single moonwalk. They collected 21.5 kilograms of lunar samples. They left a seismometer, a laser-ranging retroreflector, and various equipment. They planted a flag. They made a telephone call to the President of the United States. And they came home. The samples they brought back were analyzed by laboratories around the world. They were ancient, far older than almost any rock found on Earth's surface, because Earth's geological activity constantly destroys and recycles its rocks, while the Moon's surface has been largely static for billions of years. The oldest Apollo samples are more than 4 billion years old. Some of the ages measured pushed up against the age of the solar system itself. The next mission was supposed to be straightforward. Apollo 12 landed in November 1969 in the Ocean of Storms, within walking distance of the Surveyor 3 spacecraft that had landed there in 1967. The astronauts walked to Surveyor 3 and removed pieces of it to bring home for analysis. Scientists wanted to know if anything biological had survived 2.5 years on the lunar surface, exposed to vacuum and radiation. The answer was complicated. Possible bacterial contamination from the manufacturing process was found in a sample from Surveyor's camera, but its origin was disputed. The question of whether terrestrial microorganisms can survive extended exposure to the lunar environment was not cleanly answered by this experiment. Then came Apollo 13, April 1970. An oxygen tank in the service module exploded about 56 hours into the mission. The crew of Jim Lovell, Jack Swigert, and Fred Hayes lost the primary power and life support systems in the command module. They retreated to the lunar module, which was designed for 2 people for 2 days, and used it as a lifeboat for 4 days, while mission controllers improvised a return trajectory. They flew around the Moon, using its gravity to redirect their trajectory back toward Earth, and landed safely on April 17th. Apollo 13 became a demonstration not of what space exploration can achieve when everything goes right, but of what human ingenuity and engineering can accomplish when everything goes wrong. The mission had been planned to land in the Fra Mauro Highlands, a geologically interesting region of the near side. Apollo 14 was redesigned to land there instead, which it did in February 1971. The samples from Fra Mauro were different from the Mare basalts collected by Apollo 11 and 12. They were breccias, rocks formed by the heat and pressure of ancient impacts, and they carried information about the Moon's early bombardment history. Some of them were dated to the period of heavy bombardment, the era around 3.9 billion years ago, when the inner solar system was being saturated with impacting objects, and their composition gave scientists clues about what was hitting the Moon and Earth during that period. Apollo 15, July 1971, was the first of what NASA called the J missions, the extended scientific missions designed to maximize scientific return. The astronauts had a lunar roving vehicle, a battery-powered electric car that allowed them to travel several kilometers from the landing site. They landed at Hadley Apennine, at the base of the Apennine mountain range and next to Hadley Rill, a sinuous channel cut into the surface by ancient flowing lava. They drove to the rill's edge and photographed the exposed rock layers on its walls, reading the geological history of the region in cross-section. They drilled deep into the surface and extracted a core sample that recorded 500 million years of the Moon's history in its layers. They collected 77 kilograms of samples. Apollo 16, April 1972, landed in the Descartes Highlands, the only Apollo mission to land in ancient highland terrain, rather than in or near the Maria. Scientists had predicted before the mission that the highlands at this location would contain volcanic rocks, specifically rocks called creep basalts, that would tell them about a specific kind of ancient volcanic activity. They were wrong. The rocks at Descartes were impact breccias, formed not by volcanism but by the cumulative effect of billions of years of impacts. It was a significant revision of the models. The highlands that looked volcanic from orbit were actually impact-modified terrain. The mission disproved the hypothesis it was sent to test, which is exactly what science is supposed to do. Apollo 17, December 1972, was the last. Commander Gene Cernan, Command Module Pilot Ron Evans, and Lunar Module Pilot Harrison Schmitt, the only professional geologist to visit the Moon, landed in the Taurus-Littrow Valley. They spent more time on the surface than any previous mission. They collected more samples than any previous mission, 110 kilograms. Schmitt, trained to read geology in the field the way a doctor reads a patient's symptoms, identified orange soil near Shorty Crater, a layer of glass beads formed by an ancient explosive volcanic eruption billions of years ago, preserved under a thin cover of grey surface material. The orange soil was a genuine geological discovery made in real time on the surface of the Moon by a trained geologist who knew what he was looking at. Cernan was the last person to walk on the Moon. He stepped back into the lunar module on December 14, 1972. No human being has been to the Moon since. The Apollo program returned 382 kilograms of lunar material across 6 landings. The samples were distributed to laboratories around the world and have been studied continuously since 1969. New analyses are published every year. New discoveries are made in samples collected half a century ago, using analytical techniques that did not exist when the samples were collected. The Apollo samples are not a solved archive. They are an ongoing scientific resource that keeps giving. The Soviets, who never landed cosmonauts on the Moon, pursued robotic sample return missions that were remarkable engineering achievements in their own right. Luna 16 in September 1970 became the first robotic mission to land on the Moon, collect samples automatically, and return them to Earth. It brought back 101 grams of lunar soil from the Sea of Fertility. 101 grams, less than a quarter of a pound. But it was the first robotic sample return from another world. Luna 20 and Luna 24 followed in 1972 and 1976, returning additional small samples from different locations. The Soviets also deployed 2 robotic rovers, Lunokhod 1 in 1970 and Lunokhod 2 in 1973. These were remarkable machines. Lunokhod 1 operated for 322 Earth days and traveled 10.5 kilometers across the lunar surface. Lunokhod 2 covered 39 kilometers in 4 months. They carried cameras, scientific instruments, and laser retroreflectors. The retroreflectors on both Lunokhods are still functional. Scientists on Earth fire laser pulses at them and time the return to measure the Moon's distance with millimeter precision. 50-year-old Soviet hardware on the surface of the Moon is still being used for scientific measurements. After Luna 24 in 1976, there were no more missions to the surface of the Moon for over 20 years. The space race was over. The Cold War was winding down. Budgets shifted, interests moved elsewhere. The gap was filled in the 1990s. The American Clementine mission in 1994 was a military spacecraft that mapped the Moon from orbit, using instruments designed to test sensor technologies for ballistic missile defense. It produced the first global topographic map of the Moon, the first global multispectral image map, and found the first credible hints of water ice at the South Pole in the form of anomalous radar backscatter from permanently shadowed craters. The discovery was controversial and debated for years. The Lunar Prospector mission, launched in January 1998, orbited the Moon for 18 months and made a series of significant discoveries. It found enhanced concentrations of hydrogen at both poles, consistent with the presence of water ice in permanently shadowed craters. It mapped the distribution of radioactive thorium and potassium across the entire near side, revealing the creep concentration in unprecedented detail. It confirmed the presence of the ancient magnetic anomalies. And when its mission ended in July 1999, it was deliberately crashed into a permanently shadowed crater near the South Pole, the hope being that the impact would release water vapor that could be detected from Earth. No water vapor was detected, but the data it collected changed the understanding of the Moon fundamentally. Europe entered lunar exploration with SMART 1, launched in 2003, which spent more than a year in lunar orbit using an ion engine to gradually raise its orbit from Earth to the Moon. It was a technology demonstration mission that also conducted science, mapping the surface in infrared and identifying calcium, aluminum, silicon, and iron in the crust. Japan sent the Kaguya spacecraft to the Moon in 2007. Kaguya, also called Selene, was Japan's most ambitious space science mission to that point. It carried 14 instruments and 2 small sub-satellites deployed in lunar orbit. It produced high-definition video footage of the Moon from orbit that, when broadcast, was unlike anything the public had seen before. It produced the first direct measurements of the Moon's gravity field on the far side, using the relay satellite to maintain communication. It mapped the lunar surface in detail, and it found lava tubes, large subsurface tunnels formed by ancient lava flows, where the outer shell solidified, while molten lava continued to flow through the interior and eventually drained away, leaving a hollow tube. These lava tubes, some of them large enough to contain a city, could in principle shelter future human inhabitants from radiation and micrometeorite impacts on the surface. India's Chandrayaan-1, launched in 2008, carried the Moon Mineralogy Mapper instrument from NASA that ultimately confirmed water ice at the poles in 2018, 10 years after the spacecraft's mission. The instrument's data was in the archive for a decade before the analytical technique was developed to extract the definitive confirmation from it. A decade-old dataset reanalyzed with new methods, producing one of the most significant discoveries in lunar science. Chandrayaan-1 also made another discovery that has been less widely publicized, but is deeply significant. It found evidence of water molecules on the surface of the Moon in sunlit regions, not just in permanently shadowed polar craters, on the sunlit surface itself. The surface of the Moon in direct sunlight absorbs water molecules from space, holds them briefly, and then loses them as the surface heats up and re-radiates them. This finding, confirmed by multiple independent analyses, means the Moon's surface is cycling water molecules constantly, picking them up from solar wind interactions and losing them again, in a process that is still not fully characterized. China's Chang'e program began in 2007 with Chang'e-1, an orbiter that mapped the surface and crashed into the Moon in 2009. Chang'e-2 followed in 2010, also an orbiter, which after completing its lunar mission, went on to fly by the asteroid Tutatis. Chang'e-3, in December 2013, was China's first lunar lander, and it deployed the U-2 rover, the first wheeled vehicle to operate on the Moon since the Soviet Lunokhod 2 in 1973. U-2 traveled on the basaltic surface of the Sea of Rains and used a ground-penetrating radar to look beneath the surface for the first time from a surface vehicle. It found multiple distinct geological layers in the subsurface, a more complex stratigraphic record than the pre-mission models had predicted. Chang'e-4 in January 2019 was the first spacecraft ever to land on the far side of the Moon. It touched down in the von Karman crater inside the South Pole Aitken Basin. For the first time in history, a spacecraft was sitting on the ground we have been talking about tonight. The mission deployed the Yutu-2 rover, which has been operating ever since, and as of 2025 has traveled more than 1.9 kilometers across the far side surface. It has been operating for more than 6 years, far exceeding its planned lifespan. Yutu-2 has made discoveries that have complicated and enriched the picture of what the far side is made of. Its ground-penetrating radar found subsurface layering in the von Karman crater that indicates a complex history of multiple lava flows, impacts, and regolith accumulation over billions of years. Its spectrometer found minerals consistent with material excavated from deep in the lunar mantle by the South Pole Aitken impact itself, the first direct detection of mantle material at the surface anywhere on the Moon. The largest impact in lunar history brought material from deep inside the Moon to the surface, and Yutu-2 drove up to it and analyzed it. India's Chandrayaan-3 mission succeeded in August 2023, where Chandrayaan-2's lander had failed in 2019. Chandrayaan-3 landed near the lunar South Pole at a latitude of about 69 degrees south, the highest latitude ever reached by a lunar lander. Its Vikram lander and Pragyan rover operated for 1 lunar day, approximately 14 Earth days, before the lunar night ended their solar-powered operation. In that time, they made measurements of the surface temperature, composition, and physical properties near the South Pole. Chandrayaan-3 found sulfur on the Moon's south polar surface, not just detected from orbit, but directly confirmed on the ground. It also found aluminum, silicon, calcium, iron, titanium, manganese, oxygen, and chromium. The surface composition near the South Pole was different in measurable ways from the compositions studied at lower latitudes by Apollo and other missions. The South Polar region has its own distinct geology. The lander's thermal sensors made a measurement that surprised the team. The surface temperature varied dramatically with depth. Just a few centimeters below the surface, the temperature dropped by tens of degrees compared to the surface itself. The Moon's surface insulates extremely well, and the shallow subsurface maintains a dramatically different thermal environment from the surface exposed to sunlight. This has implications for any mission intending to drill into the South Polar surface, as the thermal environment changes rapidly with depth in ways that equipment must be designed to handle. NASA's L-Cross mission in 2009 deliberately crashed a spent rocket stage into a permanently shadowed crater near the South Pole and analyzed the debris plume with a following spacecraft. The impact excavated material from the crater floor and sent it up into sunlight, where spectrometers could analyze it. The results were definitive. Water ice confirmed. Also detected were hydrogen sulfide, ammonia, sulfur dioxide, ethylene, carbon dioxide, methanol, and various other compounds. The crater floor was not just icy, it was a chemical warehouse. Billions of years of cometary and asteroid material, preserved in the cold, accumulated into a diverse chemical mixture that included not just water, but a complex collection of volatile compounds. The diversity of that chemical mixture has profound implications. Water from comets delivered to the Moon over billions of years may have a distinctive isotopic signature, a specific ratio of regular hydrogen to heavy hydrogen, called deuterium, that would tell us about the composition of the comets that delivered it. If that signature matches the water in Earth's oceans, it tells us that the same comet population that watered the Moon also watered Earth. If it does not match, it tells us that Earth's water came from a different source than the Moon's. The Moon's polar ice is a laboratory for understanding where Earth's water came from, and it has been sitting there preserved in the cold for billions of years. NASA's Lunar Reconnaissance Orbiter, launched in 2009, has been in continuous operation for more than 15 years as of 2025. It has produced the most detailed maps of the lunar surface ever made, including maps of the permanently shadowed regions using radar and thermal imaging rather than visible light. It has identified the coldest spots on the moon, measured the radiation environment at the surface, mapped ice-bearing regions at the poles, and returned an archive of data that scientists are still actively working through. LRO has been so productive that it has been given multiple mission extensions, a 15-year mission that was planned for 1 year, a spacecraft that keeps returning valuable science and keeps being funded to continue. The picture that has emerged from all of these missions together, from Luna 1 in 1959 to Chang'e 6 in 2024, is not the picture that scientists expected at any point along the way. The moon that the first spacecraft visited was simple in the imagination. Rocky, dead, unchanging, easy to understand in outline even if the details needed filling in. The moon that 65 years of exploration has revealed is something else entirely. It is geologically complex. Its two sides are fundamentally different in ways that have not been explained. It has granite where granite should not exist. It has a buried impactor in its mantle. It has ice in its polar shadows. It has magnetic anomalies that remember impacts that happened 3.9 billion years ago. It has water molecules cycling across its sunlit surface. It has lava tubes large enough to shelter cities. Its interior is warmer on one side than the other. Its chemistry is concentrated on the near side and depleted on the far side in ways that shaped everything about its subsequent evolution. Every mission has answered questions and raised new ones. Every landing has produced data that the models did not fully predict. Every sample has contained surprises. The moon is not a solved problem. It is a problem that has gotten more interesting, more complex and more mysterious with every step we have taken toward it. And we have been stepping toward it for 65 years. We have orbited it, crashed into it, driven across it, drilled into it, and brought pieces of it home. We have mapped it from every angle at every wavelength. We have studied it with instruments that can detect parts per trillion of trace elements in lunar soil. And the far side, the side that was completely unknown until 1959, the side that was not landed on until 2019, the side whose rocks were not physically returned until 2024, is still in the early stages of being understood. Most of what we know about the far side comes from orbital data. We have rocks from one location. We have a rover driving slowly across one small region of one crater inside the largest basin in the solar system. The far side of the moon is approximately 37 million square kilometers in area. We have a single rover driving across a tiny fraction of that. We have samples from a single landing site. The rest of it, all of it, has never been touched. That is where we are in 2026. After 65 years of exploration, after billions of dollars of investment, after missions by the United States, the Soviet Union, Japan, Europe, India, China, and Israel, after 6 crewed landings on the near side, after 1 robotic landing on the far side, after 382 kilograms of near-side samples and 1.9 kilograms of far-side samples. The far side of the moon is still almost entirely unexplored. The secrets that are buried there, the anomalies, the granite batholith, the buried impactor, the magnetic archive, the ice, all of it are still largely beyond reach, still waiting, still holding most of their answers. The story of how we got here is a story of extraordinary effort, repeated failure, surprising success, and constant discovery. The story of where we go next is just beginning, and what we find there will change what we know. Not just about the moon, about everything. Now let us go back, before the discoveries, before the samples, before we knew any of what we have just described. Let us go back to the beginning of the human attempt to reach the moon, because the story of how we got here is part of understanding what the far side means. And it is a story that most people only know in fragments. The first spacecraft ever to reach the moon did not land on it. It crashed into it. On September 14, 1959, the Soviet Union's Luna 2 became the first human-made object to reach another world. It impacted the lunar surface near the Sea of Serenity on the near side, making no attempt to slow down, carrying no instruments capable of surviving the impact. It was a statement of arrival more than a scientific mission. Humanity had reached the moon. We had touched it violently for the first time. But Luna 2 was not the first spacecraft sent towards the moon. It was the sixth. Luna 1, launched on January 2, 1959, had missed the moon entirely and drifted off into a heliocentric orbit around the Sun, becoming the first artificial object to escape Earth's gravity. Before Luna 1 and Luna 2, the Soviet Union had launched 3 unnamed attempts that failed before leaving Earth's vicinity. The Americans had launched 4 Pioneer probes toward the moon between 1958 and 1959, all of which failed. Before any spacecraft successfully reached the moon, 9 had already tried and failed. Getting to the moon was hard, harder than the triumphs we remember suggest. The history of lunar exploration is a history of failure as much as success, of missions that exploded on the launch pad, of spacecraft that went silent before reaching their targets, of landers that crashed instead of landing, of orbiters that returned data for a few days before being lost to technical failures. The successes we celebrate were built on a foundation of attempts that did not work. Luna 3, launched October 4, 1959, was the first spacecraft to photograph the far side of the moon. The photographs it returned were grainy, blurry, difficult to interpret, but they were the first. Scientists studying those images saw immediately that the far side was different. The absence of large dark planes was obvious even in low-resolution images. Something was different over there, something fundamental, and nobody knew why. The Ranger program in the United States was designed to crash into the moon while transmitting photographs all the way to impact. It would give scientists the first close-up images of the lunar surface, showing detail no Earth-based telescope could reveal. The program launched its first spacecraft in August 1961. Ranger 1 never left Earth orbit. Ranger 2 failed similarly. Ranger 3 missed the moon. Ranger 4 hit the moon, but its camera system had failed before impact. Ranger 5 missed the moon and went silent. 5 consecutive failures. Ranger 6 reached the moon in February 1964. Its cameras were activated. It was on course for impact. 30 seconds before it would have begun transmitting its first photographs, the cameras failed. It crashed in silence. The photographs were never taken. Ranger 7, launched July 28, 1964, worked. It returned 4,308 photographs of the lunar surface in the final 17 minutes before impact, showing detail 1,000 times finer than any photograph taken from Earth. The images showed a surface covered in craters of every size. Overlapping and nested, ancient and fresh, a world that had been bombarded continuously for billions of years. Scientists had suspected this. Now they could see it. Ranger 7 was the first American spacecraft to successfully complete its mission to the moon. It came after 6 consecutive failures. The Soviets launched the Luna 9 mission on January 31, 1966. On February 3rd, it successfully soft-landed in the Ocean of Storms on the near side, becoming the first spacecraft to land gently on the moon and survive. The question of whether a spacecraft could land softly on the lunar surface had been genuinely uncertain before this mission. Some scientists had worried that the moon's surface was covered in deep dust that would swallow any lander. Lunar 9 resolved the question. The surface was solid enough to land on. The dust was not deep enough to be a problem. Within 4 months, NASA's Surveyor 1 confirmed the finding by soft landing in the same general region of the Moon. The Lunar Orbiter program, 5 spacecraft launched between 1966 and 1967, mapped the entire lunar surface in preparation for Apollo. All 5 missions succeeded. Together, they photographed 99% of the Moon's surface, including the far side, with sufficient resolution to identify landing sites. The photography included the first photographs of Earth taken from the Moon's vicinity, images showing our planet small and distant against the blackness of space. The Apollo program began flying astronauts in 1968. Apollo 8, December 1968, carried the first humans to leave Earth orbit and travel to another world. Frank Borman, Jim Lovell, and William Anders became the first human beings to see the far side of the Moon with their own eyes. They flew around it 10 times. They transmitted television footage of the lunar surface passing below. They read from the Book of Genesis on Christmas Eve while orbiting the Moon. And they took the photograph known as Earthrise, showing Earth appearing above the lunar horizon, a blue and white sphere rising over the grey and ancient surface below. What those 3 men saw as they flew over the far side is worth describing. They saw a surface utterly different from the near side they had studied in photographs and maps. More cratered, rougher, older looking. The absence of the familiar dark Maria was stark. The far side looked like a world that had been left alone, unchanged for billions of years, which is exactly what it had been. Apollo 11 landed on the Moon on July 20th, 1969. Neil Armstrong became the first human being to stand on the surface of another world. The landing site was in the Sea of Tranquility on the near side, a smooth, dark plain of ancient lava, chosen specifically for its flatness and accessibility. Armstrong and Buzz Aldrin spent about 2.5 hours on the surface, collected approximately 21 kilograms of rock and soil samples, and returned to the command module, piloted by Michael Collins in orbit above. Those rocks were the first physical material ever returned from another world. Scientists analyzed them with every technique available, and the results were astonishing. The lunar rocks were ancient beyond what most people expected. The oldest samples were approximately 4.5 billion years old, nearly as old as the solar system itself. They were compositionally similar to Earth rocks but distinctly different, with different isotopic ratios, different trace element abundances, different evidence of their history. They had formed in a different environment, under different conditions, in a body with a different geological history. Apollo 12, November 1969, landed near the Surveyor 3 spacecraft that had been sitting on the Moon since 1967. The astronauts walked over to it and retrieved pieces of it to bring back for analysis, studying how materials had aged in the lunar environment. Apollo 13, April 1970, suffered an oxygen tank explosion en route to the Moon. The astronauts used the lunar module as a lifeboat, swung around the Moon, and returned safely to Earth, having never landed. The accident and the rescue became one of the defining moments of the space age. Apollo 14, February 1971, landed in the Fra Mauro Highlands, a region of ancient material ejected by the Imbrium Basin, impact 3.9 billion years ago. The rocks from this site were among the oldest returned by any Apollo mission, carrying the record of one of the Moon's most catastrophic early events. Apollo 15, July 1971, was the first mission to bring a lunar roving vehicle, a battery-powered car that allowed astronauts to travel kilometers from the landing site and explore terrain that would have been unreachable on foot. The astronauts visited Hadley Reel, a canyon carved by ancient lava flows, and the base of Mons Hadley, a mountain rising 4 kilometers above the surrounding plain. Apollo 16, April 1972, landed in the Descartes Highlands, the only Apollo mission to explore the lunar highlands rather than the Maria. Scientists had expected the highland rocks to show evidence of ancient volcanism. They did not. The highlands were impact breccias, rocks formed by the heat and pressure of ancient impacts. The volcanic origin theory for the highlands was wrong. The rocks corrected the science. Apollo 17, December 1972, was the last. Harrison Schmitt, a geologist and the only professional scientist to walk on the moon during Apollo, collected samples that included orange soil, volcanic glass beads formed in ancient volcanic fire fountains, which provided important information about the early moon's interior temperature and chemistry. On December 14, 1972, Gene Cernan was the last human being to stand on the moon. He said, "As I take man's last step from the surface, back home for some time to come, but we believe not too long into the future." That was over 50 years ago. After Apollo 17, no human being has stood on the surface of the moon. No human being has stood on another world of any kind. The technology that took 12 men to the moon between 1969 and 1972 was dismantled. The Saturn V rockets that could reach the moon were retired, the remaining ones placed in museums. The institutional knowledge of how to build them dispersed. The Apollo program ended. The Soviet Union launched Luna 16 in September 1970, the first robotic mission to return samples from the moon, bringing back 101 grams of material from the Sea of Fertility. Luna 17, November 1970, delivered the Lunar 1 rover to the moon, the first remote-controlled rover to operate on another world. It operated for 10 months, covering nearly 11 kilometers of terrain, returning tens of thousands of photographs and performing hundreds of soil analyses. Lunar 2, delivered by Luna 21 in January 1973, covered about 39 kilometers in 5 months, a record for planetary rovers that stood for decades. The Soviet lunar program continued through 1976, returning additional samples and performing a series of orbital surveys. Then both the American and Soviet programs of intensive lunar exploration ended. The moon had served its purpose in the space race. The political motivation that had driven the programs dissolved. Funding dried up. The moon became, for 2 decades, a place that missions occasionally flew past or observed from Earth orbit, but that no spacecraft visited up close. The long gap lasted until 1990, when Japan's Hiten spacecraft became the first lunar mission by any country other than the United States or Soviet Union. The mission had limited scientific instruments but demonstrated that a third nation had the capability to reach the moon. In 1994, the United States launched Clementine, a Defense Department spacecraft that mapped the entire lunar surface and provided the first hints of ice in permanently shadowed craters at the poles, a detection that was controversial and contested until later missions confirmed it. Lunar Prospector 1998 strengthened the evidence for polar ice and produced the first detailed maps of the moon's gravity and elemental composition, including the creep asymmetry map that showed radioactive thorium concentrated on the near side. The mission also found that the moon's core is smaller than had been thought, about 300 to 500 kilometers in radius, confirming that the moon's interior is different from Earth's in fundamental ways. The European Space Agency entered lunar exploration with SMART 1, launched in 2003, which used an innovative ion drive to slowly spiral out from Earth orbit to the moon over 14 months. The mission produced the first X-ray map of the Moon's surface and tested technologies for future planetary missions. Japan's Kaguya mission, launched 2007, was the most sophisticated lunar orbiter since Apollo, carrying 14 instruments and 2 small sub-satellites. It returned high-definition video of the Moon's surface from orbit, including footage of Earth rising over the lunar horizon that echoed the iconic Earthrise photograph from Apollo 8, 40 years earlier. Kaguya also measured the gravity field of the far side of the Moon with higher precision than any previous mission. India entered lunar exploration with Chandrayaan-1, launched October 2008. The mission included NASA's Moon Mineralogy Mapper instrument, which in 2009 detected water molecules in the lunar soil, primarily concentrated near the poles. In 2018, scientists reanalyzing Chandrayaan-1 data confirmed the presence of water ice in permanently shadowed craters at the South Pole, the confirmation published in the Proceedings of the National Academy of Sciences. The mission also deliberately crashed a small impact probe into the lunar surface to study the material ejected by the impact. NASA's Lunar Reconnaissance Orbiter, launched June 2009, remains in operation today. It has produced the most detailed maps of the lunar surface ever made, including the first complete topographic maps of the far side. Its camera system has photographed the surface at 1 meter resolution, showing individual boulders. It has measured surface temperatures, including the extreme cold of permanently shadowed craters, confirmed to be among the coldest places in the solar system. It has imaged the Apollo landing sites, showing the descent stages and equipment still sitting where they were left. And it continues to collect data as missions are planned that will land near the South Pole. The Elk-Ross mission, launched with Lunar Reconnaissance Orbiter in 2009, deliberately impacted the Cabeus crater near the South Pole with its upper stage rocket. The impact ejected a plume of material from the permanently shadowed crater floor. Instruments analyzing the plume detected water vapor, water ice, and a variety of organic compounds including methanol, ethanol, and carbon dioxide. The crater floor contained significantly more water than scientists had anticipated. And it was not just ice, but a mixture of water with other volatile compounds that had been accumulating in this cold trap for billions of years. Grail, launched in 2011, the twin spacecraft that mapped the Moon's gravity field in extraordinary detail and revealed both the crustal thickness asymmetry and the anomalous buried mass beneath the South Pole Aitken Basin. Grail was intentionally crashed into the lunar surface in December 2012. Its final act, a last contribution to understanding the Moon it had been studying. LADEE, the Lunar Atmosphere and Dust Environment Explorer, launched 2013, studied the Moon's extremely thin atmosphere, called an exosphere, and found that it contains sodium, potassium, and dust particles levitated by electrostatic forces. The Moon has no atmosphere in any meaningful sense, but it is not entirely surrounded by vacuum. China's Chang'e program began with Chang'e-1 in 2007, an orbiter that produced a complete 3-dimensional map of the Moon. Chang'e-2 followed in 2010 with higher resolution mapping. Chang'e-3, December 2013, successfully soft-landed in the Bay of Rainbows on the near side and deployed the U-2 rover, the first soft landing on the Moon since the Soviet Lunar 24 mission in 1976. U-2 operated for about 3 months before its drive mechanism failed due to the extreme cold of the lunar night, but it continued to return scientific data in a stationary position for over 2 years. Chang'e-4, launched December 2018, accomplished something no mission had ever done before. It landed on the far side of the Moon, the von Karman crater inside the South Pole Aitken Basin, the first soft landing on the far side in the history of human spaceflight. This required a relay satellite called Queqiao, placed in a halo orbit at the Earth-Moon L to Lagrange Point to maintain communications between the lander and Earth, which the Moon's bulk would otherwise block entirely. Changi 4 deployed a rover called Yutu-2, and Yutu-2 has been operating ever since. As of early 2026, Yutu-2 has been exploring the far side for over 6 years, making it the longest operating lunar rover in history. During its years of operation, Yutu-2 has driven over 1.9 kilometers across the floor of the von Karman crater. It has analyzed the composition of the surface in detail using its spectrometers. It has detected material that scientists believe may have originated in the Moon's mantle, excavated by the South Pole Aitken impact and brought to the surface. If confirmed, this would be the first direct measurement of lunar mantle material. Yutu-2 has also detected an unusual gel-like material in a small crater it investigated in 2019. Analysis suggested the material was likely formed by a meteorite impact that melted the surrounding rocks and fused them into a glassy substance. But the initial mystery of what the strange material was attracted considerable attention and reminded scientists that the far side still holds surprises, even in its surface details. India's Chandrayaan-2 mission, launched July 2019, attempted a soft landing near the South Pole in September 2019. The lander, named Vikram, was on course for a successful landing when it lost contact with ground control at an altitude of about 2.1 kilometers. It crashed. The orbiter component of the mission survived and has continued operating, contributing mapping and scientific data from orbit. India's Chandrayaan-3 mission corrected this. Launched July 14, 2023, it successfully soft-landed near the South Pole of the Moon on August 23, 2023. This made India the 4th country to land on the Moon and the first to land near the South Pole. The lander, again named Vikram, deployed the Pragyan rover. Over the following days, Pragyan drove across the surface near the South Pole and performed in situ chemical analysis using its instruments. It detected sulfur in the soil near the South Pole, the first direct detection of sulfur at this location. It detected iron, calcium, titanium, and other elements. It detected what may be evidence of ancient volcanic activity in the South Polar region. Pragyan was put into sleep mode when the lunar night arrived, roughly 2 weeks after landing. The extreme cold of the lunar night, reaching -180 degrees Celsius at the surface, was expected to be fatal to the rover's electronics. Scientists attempted to reactivate it when Lunar Day returned but did not receive a response. Chandrayaan-3 had completed its primary mission in about 10 days of surface operations, but those 10 days produced the first chemical measurements of the South Polar region from the ground. Russia's Lunar 25 mission, the first Russian lunar mission since the Soviet Lunar 24 in 1976, was launched in August 2023, just before Chandrayaan-3. Lunar 25 attempted to reach the South Pole first, but suffered an engine malfunction during its orbit-lowering burn and crashed into the lunar surface on August 19, 2023, 4 days before Chandrayaan-3's successful landing. The commercial lunar sector has also entered the picture. Intuitive Machines' IM-1 mission, carrying NASA instruments, landed near the South Pole in February 2024 using the Odysseus lander. It was the first American soft landing on the Moon since Apollo 17 in 1972. The lander came down slightly faster than planned and tipped onto its side on landing, leaving some instruments unable to operate as intended. But it returned data for several days and demonstrated that American commercial landers could reach the Moon. Firefly Aerospace's Blue Ghost lander landed successfully on the near side of the Moon in March 2025, and operated for about 2 weeks before the lunar night ended its operations. It carried 10 NASA payloads and returned scientific data including measurements of the lunar regolith, the lunar magnetic field, and the behavior of dust during the lunar sunset. ISpace, a Japanese company, attempted a landing in April 2023 that failed during descent. A second ISpace mission was launched in late 2024. The proliferation of commercial missions reflects a fundamental change in the economics and geopolitics of lunar exploration. The Moon is no longer the exclusive domain of government space agencies from two superpowers racing to make a political point. It is becoming a destination for a widening range of actors with a widening range of motivations. And China continues. Chang'e 5, December 2020, successfully landed on the near side in the Rumka region, drilled into the surface, collected 1.73 kilograms of rock and soil, and returned them to Earth. The samples were analyzed and found to be approximately 2 billion years old, significantly younger than the Apollo samples, which ranged from 3.1 to 4.4 billion years. This extended our understanding of the Moon's volcanic history, confirming that volcanism continued on the near side until more recently than previously thought. Then, Chang'e 6, June 2024, the far side sample return, the first physical material from the far side of the Moon, brought to Earth. As described earlier, those samples transformed our understanding of the Moon's interior, confirming the deep thermal asymmetry between the two hemispheres, with direct chemical evidence for the first time. NASA's Artemis program, named for the twin sister of Apollo in Greek mythology, is the return of humans to the Moon. Artemis 1, November 2022, was an uncrewed test flight of the Space Launch System rocket and the Orion spacecraft. The mission flew around the Moon and returned to Earth, testing all systems. Artemis 2 is planned to carry 4 astronauts around the Moon without landing, the first humans to travel to lunar distance since Apollo 17 in December 1972. Artemis 3 is planned to land near the South Pole, using a modified SpaceX Starship vehicle as the human landing system. The landing sites selected for Artemis 3 are at the rim of the South Pole, near permanently shadowed craters on the edge of the South Pole Aitken Basin. The astronauts will operate near the boundary between permanently sunlit terrain, where solar panels can generate power, and the edges of the permanently shadowed regions where water ice may be accessible. They will collect samples from material excavated by the South Pole Aitken impact billions of years ago. They will potentially make measurements that address the ice question directly. They will stand at a location no human being has ever stood. The Lunar Gateway, a small space station planned for orbit around the Moon, will serve as a staging point for future missions. It will allow astronauts to travel to and from the lunar surface multiple times from a single orbital outpost, rather than making the entire journey from Earth each time. It will be assembled in stages with contributions from international partners, including the European Space Agency, Japan, Canada, and the United Arab Emirates. It is intended to be a permanent human presence in the Earth-Moon system for the first time. China has announced plans for an International Lunar Research Station, a long-term facility at the South Pole of the Moon developed in partnership with Russia and other nations. The station is planned in phases, beginning with robotic precursor missions and culminating in human habitation. The South Pole is the target because of the water ice, and because the peaks of eternal light at the pole receive near continuous sunlight for solar power generation. Two major space powers are both planning permanent presence at the South Pole of the Moon, both focused on the same region, the South Pole Aitken Basin Rim, the permanently shadowed craters, the water ice, the ancient material. The same scientific and strategic location, The moon is becoming a destination again, not as a one-time achievement, but as a place humans intend to stay. 65 years after Lunar 3 first photographed the far side. 53 years after Gene Cernan stepped off the moon and the last human being left its surface. The far side is now where multiple nations are focusing their deepest attention. Not just out of scientific curiosity, but because the water ice there, if accessible in sufficient quantities, could change the economics of the entire solar system. Water can be split into hydrogen and oxygen. Hydrogen and oxygen are rocket fuel. A refueling station at the south pole of the moon, using locally produced propellant derived from ancient ice, could make the entire solar system reachable in ways it currently is not. That is not science fiction. That is the current stated goal of multiple national space programs and dozens of commercial companies. The ancient ice preserved in the permanently shadowed craters of the far side. Ice that arrived on comets and asteroids billions of years ago. Ice that has been sitting in the dark, waiting since before complex life appeared on Earth, may become the fuel that takes humanity to Mars. The far side of the moon is not the back of a dead rock. It is an archive of the solar system's earliest history, a record of impacts and chemistry and magnetic fields and thermal evolution that have been preserved in silence for billions of years. And it is potentially the key to the next chapter of human expansion into space. We have just begun to read what is written there. Every mission that goes to the moon, every sample that comes back from it, every year that Yutu-2 drives across the floor of Von Karman crater, adds new pages to that archive. Chang'e 6's samples turned one hypothesis into confirmed fact. The first complete chemical map of the moon, published just weeks ago in early 2026, showed us the full picture for the first time. And what we have found is strange. Strange enough to make experienced scientists say they were puzzled. Strange enough to require new explanations. Strange enough that the textbook models do not fully work anymore. Strange enough that the more we look, the more we realize we are only beginning. Now let us take a step back and look at all of this together, because the picture that emerges when you lay it all out is striking. We have a moon whose two sides are fundamentally different in surface appearance, different in crustal thickness, different in chemical composition, different in thermal history, different in volcanic history. All of this documented, all of this confirmed, none of it fully explained. We have the largest impact crater in the solar system on the far side, with a massive anomalous buried object confirmed by gravity measurements sitting in the mantle beneath it. 4 billion years old, never sampled, never directly characterized, still there. We have a granite batholith 50 kilometers wide buried on the far side, where granite should not exist according to the standard models. Published in Nature, confirmed, unexplained. We have magnetic anomalies on the far side preserving a record of ancient fields stronger than the models predict should have existed. Unexplained. We have the first direct samples from the far side confirming the moon's interior is colder on that side all the way into the mantle. A deep structural asymmetry confirmed with real rock for the first time in history. We have confirmed water ice in permanently shadowed craters at the South Pole of unknown composition, potentially carrying the answer to where Earth's water came from. And we have the entire history of human spaceflight, from the first spacecraft that missed the moon entirely to the rovers still driving across the far side today, now focused on one single region, the South Pole, the edge of the largest crater in the solar system, the place where the secrets are deepest and the ice is oldest. Each one of these things individually would be a major scientific discovery. Together, they describe a moon that is far stranger and far more complex than the simple, airless rock that most people imagine when they look up at it on a clear night. The far side of the moon is not a mystery we have solved. It is a mystery we have barely introduced ourselves to. A geological archive that has been sitting in the sky, preserved in airless cold for 4.3 billion years, waiting for instruments capable of reading it, waiting for missions capable of reaching it, waiting for human hands to pick up its rocks. For all of human history, we looked up at the moon and thought we knew it. We named its craters. We mapped its surface. We landed on it 12 times across 6 missions. We drove across it in electric rovers. We brought 382 kilograms of it back to Earth. And all that time, half of it, the half that never faces us, was quietly holding its secrets in the dark. The largest crater in the solar system, a granite body that should not exist. A buried impactor still sitting in the mantle 4 billion years later. Ancient ice potentially carrying the chemical history of the early solar system. Magnetic records of fields the models say were too strong. A deep interior colder on one side than the other. All of it hidden, all of it waiting, all of it on the side we could not see for all of human history until 65 years ago. The Artemis astronauts who will stand at the South Pole in the coming years will be the first humans to stand at the edge of all of this. The first humans with the ability to reach out and pick up material from the deepest excavation event in the moon's history. The first humans close enough to drill into ice that may have been preserved since the early solar system, carrying a record of where the water came from that eventually made Earth habitable for life. We have been looking at the moon for the entire history of our species. We built telescopes and pointed them at it. We named every feature visible from Earth. We sent 65 years of spacecraft to orbit it, land on it, crash into it, and return its rocks. And still, in 2026, we are only just publishing the first complete chemical map of its surface. Only just holding samples from the far side in our hands for the first time. Only just beginning to understand what it is trying to tell us. The far side of the moon has been waiting for 4.3 billion years. We are just arriving.